Yeah, I think Barner might have said that those who can write and those who cannot, those who cannot teach. Now, I think the organizers, Purushottam and Pinaki, decided to change a little. Those who are doing some work, they will talk, and those who are not doing will conclude. So I am here to conclude because I am not doing much. But I would like to tell that this series of events are giving a great opportunity, series of this conference, which usually the physics people are not getting. There are, many other physics topics which are being discussed in various conferences, either in India and elsewhere, but fracture meetings are very rare. In fact, engineers are continuing, and I will tell that this is an irony, but before that, physicists have this international conference on fracture, which is every 4 years or so. In '84, there was one in India. I think Purushottam attended that as a student, and since then it has never been held in India. And this year it is being held in Greece, and but anyway, it is essentially for the engineers, and so there are some, the mode is a little different. Daniel Bonamy and Laura Ponceau are actually organizing a statistical physics part of that meeting, but as I told him, it's very impossible for us physicists to participate in that, because this year, thanks for the invitation, but the registration charge is €900, so it's not possible, for us to afford. So, but anyway, these kind of meetings are not there for physicists, and where there are many urgent materials to discuss and very lively subject as well. I will show that fracture studies and related one, earthquake studies, have got the, as the longest or biggest heritage in terms of a living science. It is still living, and the only one comparable is gravity research, which is at least 200 years younger than this. The first one was first study for fracture was by Da Vinci in around 1500, and I cannot convince you easily, but it is not a joke. You can see that, this is, you just do it on the internet. This is a paper which from archive, not archive, it's on the internet. Leonardo da Vinci's tensile strength tests, implications for the discovery of engineering mechanics. This is by Lund and Byrne, and this is in 2000, published, Journal of Civil Engineering and Environmental Science, and these people are from University of California, Department of Civil Engineering, and this is in 2000, Leonardo da Vinci's tensile strength experiment. And okay, let me try to show you the experiment that da Vinci did in 1500, around 1500. I don't know whether you can see it. You have a bucket full of sand. It is and it is falling from a tap which closes once there is another bucket on which this is falling. This bucket is hanging through a wire of fixed material and cross section. And if the wire fails, then the clip goes off, and then there is no more sand in it. So you can measure the amount of sand, and then you change the length of the bucket, and that way you will find as the length changes whether there is any change in the tensile strength of this material. Remember, this is one of the most intriguing observations he made, and that is more than 500 years back. The observation was it is decreasing, the strength is decreasing with the increase of the length of the wear. This is the first system size dependence of materials. Now, why this created a problem? I think it came to Gumbel and Weibull to give a general idea why this is happening. In between Griffith, Galileo also did, but you know that, I mean, Newton came much later here. He didn't do on this, but I mean, gravity started from there. These experiments were even before that, and we are actually still troubled with this kind of problems that Da Vinci observed. It's a very intriguing problem, and it has it says the different kind of statistics involved in. I mean, it's not an extensive statistics. So, let me actually, this has been indicated by many, but let me so what Griffith tried to tell is actually that was the expected thing, but this is not neither Da Vinci nor Galileo got. I mean, what Griffith said is that if you have a kind of a solid, if you have a defect of the very dominant defect of size L, and if it is a brittle material, that means fails within the linear region, then the energy density will be stress into strain. So strain is the modulus of elasticity, Y is the modulus of elasticity and stress into strain square, and L to the D is the volume from which the elastic energy will be released in some fraction of it, and that must be sufficient to produce the surfaces needed and the surface energy density. So the equality occurs at sigma c. So sigma c will go as modulus of elasticity times surface energy density by L, square root of that. This was Griffith's, that a prominent defect of size L will start propagating under stress, and that threshold should be this. And if the material is of fixed size, fixed nominally identical, then there should be fixed size of defects in the system. So that means no matter how big the sample should be, it should have the same strength, but this is what Da Vinci didn't get. So what Gumbel and Weibull tried to kind of formulate, but as statistics, was that not to get the entire thing, but something like this. Suppose you have a big sample and it has many defects. So the failure probability of that sample under stress sigma, which is the system overall is under stress sigma, this is the failure probability. So survival probability is 1 minus sigma, should be given by the survival probability of each of the defects that are there, and that should be each of them must survive. Each of these defects must survive under this stress. If all the defects survive, then only the whole sample survives. This is from where the extreme statistics is coming, and actually what Da Vinci was indicating. Because this means it is, if you assume that this probability is small, then it is minus f and this goes up, and that can be written as e to the minus volume times, say, a density of cracks or defects in the system which would start propagating under sigma. You can easily see that the survival probability decreases as the volume increases exponentially. So the system will not survive. I mean, there would be no critical threshold like this fixed if the sample size increases. And okay, what G sigma Weibel was sigma to the power some power, and G Gumbel was e to the minus some constant by sigma to the power a number, G, zeta, whatever. You can easily see that if this is the thing, then sigma c at which this probability will be finite will go as 1 upon v to the power 1 upon w. This is Weibel estimate, and sigma c Gumbel would be 1 upon log v to the power zeta or z, whatever you call. So this is, and that shows that as you increase the sample size, that could be the system would fail at lower and lower stresses, and this is exactly what they were seeing. Okay, I mean, as I said, I mean, it continued. I just collected a few of the names. Pierce introduced the fiber bundle model. I mean, there has been many discussions, and the last talk had some detailed discussions on it. Again, I mean, in the long range limit, it gives some fixed things, and in the, I mean, this is the ELS kind of model, but if you have, I mean, that means, I mean, GLS, I mean, the global load sharing, but in case it is local load sharing, then of course, again, you will come to this kind of situation. And, okay, Mott studied crack propagation velocity. Weibel we discussed. Borisnopov gave the first stick-slip, I mean, frictional model for earthquake. And still, I mean, all earth science textbooks deal with these. Soles studied rock fracture. Mandelbrot first showed that, I mean, fracture surface is the first concrete objective fractal that can be studied in the laboratory. It was a Nature paper. He also tried to do some experiments, and many of the participants here have done major experiments. I will come to them later. And what I would say that, I mean, of course, now we will come to somewhat, I mean, okay, already in 84, so we will come to somewhat recent ones. But you can see that in spite of all these things, there has been no textbook in physics which introduce, I mean, there are so many textbooks in physics, is where many of the recent and of course important topics are discussed, but fracture is not discussed in any of the textbooks. I mean, Kittell's book has a marginal mention in the last chapter of the Griffith's law, but Chaikin-Lubensky doesn't have anything, and there are no textbooks, and no student ever learned that there is a problem as, I mean, as important as it could be, and it's still a very lively problem. So many people are contributing to it, and I will try to show that how many contributions are coming every day. And yet there is no attempt by physicists to even to meet regularly to discuss about the progress, if at all. And partly this is because there is no, I mean, it's possible there were not enough important salesmen in this business, although some great names are involved in it, have been involved in it, but that is, and also I think quantum mechanics, there is no direct impact of quantum mechanics or the developments in quantum mechanics here, and that probably took away the interest from this problem, which is completely unsolved still. Now let me go to the next thing. I will come to 85. Now of course I will correct many things. Of course I don't have to justify why I had put my and Purushottam's things, Darkanjali's, Herman, then Duxbury and Leith. But I would say that there is something, because you see, if, after these 3 papers, and receipt date of this one is the earliest, I mean then this one next, and then this one. And within 3 years, about 3 times the rate of publications in statistical physics of fracture. You could check it from, I will show some of these results. From Google Scholar, the papers with statistical physics of fracture in the title, and maybe they also go to the text, I mean Google Scholar. So that number didn't go very high, but it became almost 3 times, and most successful has been this paper. I can tell you a nice story. This paper by us was in solicited communication in 84, and then early 85 it was published, and I was in Europe for some longer time, and I had no other things to tell than this. I didn't think that this is an important thing, but I mean anyway I had no other important thing to tell. So I was giving talks everywhere like this. I met Phil Duxbury in Oxford, who was finishing his PhD. He tried to understand what is this, and then I came back and I came to Cologne and gave another talk on this. Herman was there, and then there were these papers. Of course, this came later, and I had no knowledge. There was nothing, no reference to this. But anyway, this paper has this is the most successful one. But this paper has a reference to this 85 work, but not in the first version. It was that, I mean, the referee was, at least one of the referee was, this was in Journal de Physique. This is no longer there, the journal. Anyway, so Stauffer walked into my office and said that, I mean, did you not tell Hans that, I mean, this paper is published? I said, yes, I told. And did he discuss with you? He said, yes. So I think what he told me, that I have said that this paper is accepted, but conditional that this reference has to be given. So that's the way we got the reference. But anyway, after these 3, there were some impact. And then there were these, I mean, following essentially Anisul Rahman, molecular dynamic simulations. Rob Thompson and Farid Abraham, Rajiv Kalia was here, Priya Vasishtha and others. They started atomistics of fracture simulation, which gave a lot of, I mean, possibilities to check the theories. Then there were these SOC models, which were mainly addressed to, I mean, earthquake, models, and particularly this Olami et al.'s model became quite successful. Benguigui first showed how the breakdown paths could be identified. I mean, it was a nice experiment. I mean, in dielectric breakdown, the dielectrics were light emitting diodes. So wherever there was a breaking, the lights came out, so they could find out the path of the breakdown in the dielectric breakdown, random network of dielectrics and conductors. And it showed that the percolation statistics of the shortest path path, shortest gap, was not not always, and that actually explained some of the things. Anyway, that was an interesting, very intriguing work. Ravi Chandra, of course, numerically and also experiments on dynamic fracture. Langer's work, and then a big a review on this numerical study of the Langer and company, I mean, on the Baryshnikov model earthquake, gave a major, I mean, boost to the subject. And he also, of course, together with, I mean, there are many such studies on dynamic fracture. Kutmalai and many of the colleagues, Bonami also was with them, and Poso, and then Renetoso and Santusi, Malloy, they made a important study on the surface roughness experiment, and which was, as I said, which was kind of indicated first by, Mandelbrot. And Sornet brought it to the physics community. Sornet in '89 brought the fiber bundle model to the physics community in a published form. There were some talks by, anyway, I forgot the name, I mean, but anyway, and then there was a beautiful calculation by Alex Hansen and Per Hamer in '94 about the avalanche size exponent in the Daniels model. I mean, okay, I forgot, I mean, Pierre first gave the model, and then in the mean field limit where the, okay, I will not go into that details. So, in that limit, in the Daniels limit, I mean this Daniels limit, okay, not Daniel Bonami, but I mean Daniel in 45 first made the mean field version of this precise, and gave the equation to determine the strength, but not the dynamics. That was not possible with that thing. I think the first one interesting dynamical study was by Henson and Hammer. Zaperi, Ray and Stanley gave a provoking idea of this first order transition in this fiber bundle model, but that was not correct, sorry. And I think we first showed that it is not, and it's actually a continuous transition, and but I think we gave completely analytic solutions for these kind of systems for the entire dynamics in that, of course, mean field limit. Randall, Turcotte, Corral, Professor Kawamura and Professor Hatano are they here, Sarvokov, they are actually following the statistical physics of earthquakes, and there are some cross literatures coming out, and that's a great thing. And then the eventual kind of bridging between this kind of observation that, I mean, where it is I mean, where it is essentially Griffith-like or nucleation-like, to a kind of extended thing like percolation. This is not entirely thing, but I mean, whenever there is a say this kind of avalanche, I mean power law avalanches, that kind of situation, this crossover was not very easy from, I mean, it was an extension of this paper with a different kind of disorder, and then they showed, Shetna and Zaperi, that there is indeed a crossover, and okay, I mean, it's settled that, I mean, some of the percolation models that we were expecting that will show eventually extensive behavior will never show, it will remain on the nucleation side. Anyway, so this is as far as some of the summary that I would, sorry, I mean, this is just a personal way of doing. Now I will try to give you some statistics. I mean, okay, so some of the recent books and reviews are here, and I tried to collect Amazon books from Amazon. If you try to find out from 2007 onwards, how many physics of fracture books. Now they will probably, I don't know how Amazon collects, it is not ever written. Most likely they go from, I mean, they take something from the material. For each book there is some blurb from that is also available on Amazon site. So from there, not only the title but others, so they find out physics of fracture, you will find 416 books. Statistical physics of fracture, 18 books. This is from 2007, for the last 10 years. Physics of earthquake, you will have 390 books since for the last 10 years, I mean until 2016, end of 2016. Statistical physics of earthquakes, 10 books. Some of these books are probably here also, Kagan, Statistical Physics of Earthquakes. And compare it with something very established, but much, as I can say, I mean, physics of liquid crystals was not existing 50 years back. And this is fracture is, as I showed, is 500 years old subject. Still there are so many books and things. Yet, I mean, physics of liquid crystals was awarded Nobel Prize, I mean, not physics of liquid crystals, but Dujan got Nobel Prize in 1991 for physics of liquid crystals. For the last 10 years before Nobel Prize, there were 116 books. If you take statistical physics of liquid crystals, then only 10 books. Compare with physics, physics of fracture or earthquake. Just for, I mean, this is of course statistical physics, but just for, I mean, you may say that these are much older. You can see that physics of graphene, a very popular topic. Until the Nobel Prize in 2010, only 8 books were there. Just as a comparison, I mean, just one comparison which is easy. Reviews of modern physics published. On fracture, 4 reviews until 2016. These are the years. Earthquake, 3 reviews up to 2016. Liquid crystals, 3 reviews up to Nobel Prize. Graphene, 3 reviews up to Nobel Prize. And what I am trying to tell is that it's not that, I mean, there are not even major attempts by scientists, but for some reason, now I come to much more detailed statistics. Fracture and earthquake studies. Now you can do it various ways. I mean, you can take it from ISI Web of Science data. Now this Web of Science data actually looks into title, abstract and keywords. So whereas Google Scholar data actually is much more extensive because they go into that text also, and these are only papers. You can see, no, I mean, it also goes to books and documents if it is there. So anyway, from Google Scholar data, I think there are some extensive data you can see. Physics of fracture is growing. There were some temporary things, I mean, then it is again. Now typically, try to remember, it is about 45,000. And physics of earthquake is a little less, about 18,000 or so. Somehow it went down after 2013. There is a little lull. And if you make it statistical physics of fracture, then of course the numbers goes down from 45,000 to about 11,000 or so. And by a factor of 4, I think more or less it has come down, or not. It's about 11,000, it's about 5,000, no. So it's just that. Now compare this with liquid crystals, and again I would rather not. I have given from 2002 to 13. Now Nobel Prize for graphene was given here, and this is Google Scholar data, so it is much more extensive. So liquid crystal here, This is the Nobel Prize year, and it was only less than, I mean, some 3,500 or so, and physics of liquid crystals, just simple liquid crystals, I mean, that includes so many chemistry and other things, even that was only 7,000. Whereas, if you go to physics of fracture, physics of fracture, then it is in Google Scholar it is about 45,000. Statistical physics is, even statistical physics is more than physics of liquid crystals. And even for graphene, I mean, which is a very popular one, sorry. It has nothing to do with any statistical physics, but even total physics of graphene papers were, before Nobel Prize, it was for the 10 years, it went to maximum of 18,000 or something. So what I am trying to tell, there has been no dearth of atoms, but there is no interaction among the, each of the fibers are, each of the scientists are independently trying whatever. There is no real meeting, no discussion. People contribute because, also there seems to be some money, because otherwise we will not be able to continue these things. But the only thing is there is no interaction whatsoever. There is no, this kind of general discussions to see where it is going. Why so, after so many years, even starting from Leonardo da Vinci, a simple observation by da Vinci is not there in any of the textbooks. Neither Kittel nor Chaikin-Lubensky. Chaikin-Lubensky, at least soft mechanics matter, it should have a chapter on fracture. It doesn't have. And nobody cares. Nobody actually is worried why it is not there. I think fiber bundle is a beautiful model for all. It is really, you can take it to the level of engineering mechanics, and then its beautiful physics can be studied. Yet there is nothing in the textbooks. Students do not get to learn, and they are not motivated. They do not. Also, if well, I can tell from my experience, students doing research in fracture are not taken very seriously. It is thought that it's a dull subject. It has no future really. It's neither engineering and certainly not physics. And if this continues, there would be nothing. There would not be major progress. But what I am saying is that we should think seriously why we are landing to such a situation which is so rich, has a huge heritage and a huge potential. If we can really understand these things, and if it can be extended towards earthquake, which is always stirring and which occurs whenever we are least prepared, because we do not have a clue. And it cannot be more staggering a problem in any other quantum problems that we are so fascinated about. Yet, it has such a beautiful prospect, yet, and also so many people working, yet there is no dialogue, nothing is happening. Thank you.
So, thank you, Professor Chakrabarty, for thoughtful remarks. If anybody wants to say a few words, yeah.
I just wanted to mention that among the engineering groups, there are a lot of organizations and meetings which are regularly organized. For example, the International Congress. No, I just wanted to mention 2 or 3 of them. For example, the International Congress of Fracture, which was started in 1965, right? The first one took place in Sendai. That's actually a Congress, and it's got a president, it's got office bearers, and meetings are held once in 4 years. And the next one is going to be in Greece, in Rhodes. That's going to be in June.
I was mentioning that.
And it's a huge conference. There are some 1,000 people.
But also it has 900 euro registration charge.
I know. But let me just complete. See, usually the numbers are of the order of 1,000 or so. There's one which was held in India, 1984.
84,
and it's by a bidding process. So the Congress, during the Congress, various countries would bid for it, and there is a voting that is done. India is also a representative. I have voted once on behalf of India. So you vote and then you select the next. So it goes around the globe. Besides that, there are other, for example, European Congress of Fracture. European Congress of Fracture is also held once in 4 years.
4 years.
Yeah, I think it's 4 years or 2 years, I'm not sure. But it goes by rotation. And many of the European countries have their own fracture societies. Like, for example, Italy has. And they have meetings. Last time, I remember we had one person from Italy who was there in this similar frac meet. I think Purushottam would remember. You had invited one person from Italy, remember? And he was involved, I forgot his name. He was involved in the...
As you mentioned, Italy is very active in the streets, so
Yeah.
it's happening very so exactly which one I meant.
Yeah, so those many of the European countries have their own fracture societies and they have meetings. Now, from the context of India, very recently, there is a Structural Integrity Association which was started. This was about a year back by Professor Ramarao, who was one of the organizers of ICF4, the Congress in Delhi.
ICF4 was in Bhopal,
no, it was in
Bhopal?
Delhi. It was in Delhi.
It was in Delhi.
And Professor Ramarao and K.N. Raju, these were he was at NAL at that time.
Yeah.
And these were the two people who organized it. Now they have Ramarao has started the Structural Integrity Association, and they are supposed to hold meetings on a regular basis, at least to bring groups in India which work on fracture research together.
And you are certainly,
and the first meeting was held in Bangalore, but I was not part of it. But
no, but I would request you through you. Physicists should be invited to that possible, and also the physics community should have their own discussion meetings. We are lacking everywhere. Not just in India. Everywhere. I think maybe some of you can tell.
No, but I think people in, for example, in France and Norway, there is a community which meets very regularly every year. I think Santucci and Malloy, they organize meetings at least once.
Yeah, that is. These are actually personal. Some personal groups. Personal collaborators. They are meeting. Yeah. Yeah, but not an international kind of meeting where others can go. We go to so many international meetings on any other subject that we can think of, but not for fracture. Physics of fracture or statistical physics of fracture for that.
So among your remarks, you regret that there's not more communication between scientists, at least on the physics side, on fracture, and you also regret that there's not more systematic introduction to students in physics or nonlinear physics or statistical physics or maybe in geoscience or something to bring. So what's the most important?
Is it not surprising that two of the very, Kittle's book has, since 50s, it has been a kind of standard textbooks everywhere for condensed matter physics. There was no mention except that there was a Griffith law, marginally mentioned. There was nothing else. There is nothing else. Of course, that's not possible because the recent one is Chaikin-Lubensky. It doesn't have anything on fracture. But that's not a very standard textbook. The thing is, it has to come to standard textbook. There are books where it is there. Fracture is actually in some. There are books. I showed some of the books also here. Alex has a book, Lucas, and you have books. But these are not standard textbooks yet. I'm sure these are very important because from here people will collect things and put there in the standard textbook on condensed matter physics and things like that. But it has to be because it is long overdue. It is the oldest, I mean, as I said. I mean, okay, I forgot to make a joke that gravity research is so popular that even our Prime Minister understands that, and a huge amount of money, some 1,000 crores taken from all of us probably out and given to gravity research. I think the much more important would be some fracture research to get that money. Anyway, what I'm saying is this is much more important. Earthquake research for sure, but even fracture research in this country deserves much more attention. Not only in just this country, everywhere, but we do not have that much interest. I mean, and I think the most important thing is that the students do not get to learn. I mean, unless they are getting to learn what is this subject is.
I mean, I don't know what's most important between the communication between scientists and the teaching part, but I see that one of the difficulties too is that I'm by formation a physicist, and I'm sitting in the geophysics department, and I know very often that most of the physics students don't have a lot of knowledge of what are the observations on earthquakes, and most of the geophysics students or seismologists that study earthquakes one by one with different techniques don't have so many tools in terms of statistical physics or statistics. So maybe there is something to do as well into bridging the teaching of scientists that are interested in both fields.